How is the metal sector? Everything is going up again.
Yeah, see the
metal sector, it
disruption.
is actually golden era for them.
Yeah,
And because of the
particularly
current conflict, also, I think they are gaining.
yeah, the disruption in Ukraine and Russia is causing a disruption in the supply chain of many things. So there is a demand that has suddenly come up,
and they were major suppliers.
driving up prices.
Yeah.
But all these commodities are cyclical. So
Absolutely. Yeah.
Only the share market is going down,
yes,
and commodity prices, including oil.
gold has gone up.
Naturally, if share market will go down, then gold will go up.
Yeah. Oil prices are going up now. It will go up again or more.
It'll go up again. Yeah.
And worst is edible oil.
Yeah, that may be just a temporary thing.
No, it is not temporary. Our major supplier of sunflower oil is Ukraine and Russia.
Oh.
I think Russia is giving discounts to India.
Yeah, it is everywhere it will go up. So now it is time to start.
Yeah, maybe 1 minute in my watch.
Okay, we'll go by your watch.
It's okay.
5:59.
So people might join in. So that's why we will take about 5 minutes to introduce and other things. So we can start also if you wish.
Yes. Actually, we'll start. On behalf of Indian National Academy of Engineering Bhubaneswar chapter and my own behalf, I extend you all a very hearty welcome to this fourth distinguished lecture series. And we have been organizing practically for last 3 months one such lecture, and it so happened that it was all on 7th of the month, and this is the fourth one in that series. And this particular month, we'll definitely have two, one tomorrow also, and maybe the third one towards the third week of this month. And next month onwards, we'll have 2 lectures every month. So, and one more thing I'm happy to say, that our small chapter, INAE Bhubaneswar chapter, most likely will host the annual convention in December 2022, and we would like to make it a grand success with participation of everybody. So that is one thing. And in this lecture, our distinguished speaker is Dr. Bhattacharya. He is the Chief of R&D in Tata Steel. Of course, with this little thing, I would really like that our Honorable Vice Chancellor of SOA University, Professor Ashok Mahapatra, to say something about this university, and they are our co-organizers for this thing. So may I request Professor Mahapatra to please chip in. Professor Mahapatra, please.
Can you hear?
Yes, we can hear. Please go ahead.
Good afternoon, Professor Acharya, all our guests, Dr. Bhattacharya, Director of the IIMT, and friends. It is a great pleasure that we are having this series of lectures organized by our Odisha chapter of engineering, Indian Institute of Engineering Odisha chapter. And I thank Dr. Acharya for organizing excellent lectures. Regarding the university, it is a collaborative program, and we have been doing many lectures over last 1 year, and it is one of the lecture organized at a very high level by the eminent speakers on the field of engineering. I'm very happy that this is slowly picking up and many people are joining this lecture. Regarding the university, this is a very young university, and it's only less than 25 years old. However, our trust is more than 25 years old. Today we have got university which is ranking 20 in India by NRFA ranking, and in Asia QS ranking it's between 400 plus, and world ranking is 800 plus university. And we have our very nice engineering services, which is School of Engineering, which is ranking 31 in the country, and medical school ranking 20 in the country. Dental is ranking 14 in the country. Overall, we have 10 institutions, including the veterinary. We have also started a medical technology, which is lab technology, OT technology, radiological technology. And we have around 14,000 students and 13,000 teachers with a ratio of 1:9. And we have 47% students are girl students and 37% teachers and ladies. So we have no gender bias like that. We are trying to achieve a greater height. We have ranked already highest ranking by NAC in 2009 and 2015. We are waiting for the third accreditation by NAC. All the laboratories are accredited BLS 3 and hospital accreditation system. And during the COVID period, we had a wave 1, 2,400 beds, and wave 2, we had 2,700 beds in 6 districts of Odisha. Probably we treated more than 50,000 COVID patients. So, and our hospital is one of the cheapest in the state of Odisha. And if you look at the ranking of medical hospital ranking, many of our hospital departments, medical departments, rank number 1 to number 3 in the eastern region, India. We are now taking 250 medical students, more than 2,000 engineering students, around 140 PhD students, and postgraduate student, MTech, MSc Biotechnology, Hospital Management, and also Master in Business Management, Master in Hospital Management. They are numbering more than 1,000. So our university has put a place in not only Eastern India in India, and we are trying to get a better ranking in incoming years. And these lectures are going to benefit our teachers and students, and I hope everybody will benefit from our very high quality lectures by our eminent speakers. This time the speaker is Mr. Bhattacharya from the Tata Steel. I'm sure he has a vast experience. As I know Professor Acharya with his vast experience in engineering, teaching and administration, he will always get an eminent speaker which can benefit, which will have to benefit our student and teacher. So I thank Dr. Bhattacharya to accept our invitation. I thank Professor Acharya and Director of IIMT. They are all putting their whole heart and brain to this lecture program. Once again, I thank all of you being here to attending this lecture. Thank you. Vande Utkal Janani. Thank you. Jai Hind. Namaskar. I think it's okay. I have finished.
So may I now request,
Acharya.
hello?
Yes, I'm hearing.
Okay. Everything fine. So now may I request Professor Basu to speak something about his own institution and also to introduce Dr. Bhattacharya, because he is the best person who can introduce Dr. Bhattacharya. Okay.
Good evening, all the attendee of this of this webinar, which is conducted by IINE Bhubaneswar chapter in cooperation with IMT Bhubaneswar and SOA University. And thank you, Dr. Debashis Bhattacharya, for accepting to speak in our gathering at Bhubaneswar INAE chapter. Before I go introduce the speaker, I'll just speak a little bit about my institute. Our institute started in 1964. We are about 68th year, going to celebrate next year the 68th year of our existence. And this institute works known at one point of time as Regional Research Lab. And then in last decade, in 2007, changed this vision and mission into only working towards minerals and materials. And so the name is changed to Institute of Minerals and Materials Technology in 2007. So we cater mostly in the mineral sector. And as you all know that Orissa is one of the uh, highest mineral rich states among all the states in India. And adjoining states, Jharkhand, Chhattisgarh, Andhra, Karnataka, little far off, Tamil Nadu, and Madhya Pradesh, Rajasthan, and Gujarat. There are northeast as well, all having a lot of minerals, and we do a lot of mineral ore geology, mineralogy, mineral processing, and then extractive metallurgy work. We are working also on material development, advanced material technology, and environment related issue in our lab. We work with Tata Steel and all the other steel companies like Jindals and SAIL, and also non-ferrous like aluminium, zinc, copper. We work a lot on polymetallic nodule, which is a seabed nodule, polymetallic sulfides. And in material sectors, we are working on a lot of energy materials and devices. And of late, uh, we are gaining strength in circular economy and green processes. We are heavily working last 2 years on rare earth sourcing, whether primary or secondary sources. And of course, we keep track of environmental issues related to mineral processing and others. With this introduction, I would I will introduce today's speaker, Dr. Debashis Bhattacharya, who obtained his BE Metallurgical Engineering from Jadavpur University in 1986. Followed by that, he completed MTech in Metallurgy from IIT Kanpur in 1989. Thereafter, he moved to UK, University of Cambridge, to do his doctoral or PhD in Material Science and Metallurgy from University of Cambridge. Followed by that, he did his postdoctoral fellowship in Rolls-Royce University Technology Center at Cambridge. After that, he joined Tata Steel, and he joined Tata Steel R&D in 1996, headed the as the Chief Research and Development Scientific Services till 2009. But in between, he went back to Birmingham to do another postdoc between 2000 and 2002. Uh, he also involved Tata Steel Europe as a group director, research development and technology for Tata Steel Group. Uh, he of course, his area is interest is mostly on development of material and associated technologies, fracture fatting materials, physical metallurgy, uh, rolling, and many others, especially AI, artificial neural network, and many others. He has more than 50 international reviewed paper, 20 patents, and many more. He also worked in mineral beneficiation, hydrogen generation, or low-cost hydrogen generation. Of late, he's concentrating on CCUS and implementing CCUS in Tata Steel blast furnace. So a lot of ideas like coating. He's been working on graphene coating of rebar, um, uh, composite materials development, many more. He's a fellow of Indian National Academy of Engineering and fellow of Indian Institute of Metals. Also, he's a visiting professor at the Imperial College London, University of Warwick, UK, University of Science and Technology, Beijing in China. He's currently in the board of Tata Steel Long Products, chairman of CII Eastern Regional Subcommittee and Task Force on Startups, and leads CII's Advanced Materials Subcommittee. He's also a member of Bengal Chamber of Commerce, a chairman of expert group of Empowered Technology Group of Government of India, and many more. And you can see that he is being champion in many areas. And today we are really lucky to have him with us. He will be giving lecture or webinar, India's self-sufficiency in materials for 21st century. With this introduction, I thank you again, Dr. Bhattacharya, and kindly give your deliberation. Thank you.
Thank you, Professor Basu. Can you hear me clearly?
Yes.
Great. So thank you, Professor Basu and Professor Acharya, Professor Mohapatra, for your kind invitation and the opportunity of given me to speak here to this august gathering. It's my pleasure and my honor to be addressing such an eminent gathering with the INAE chapter, the Bhubaneswar chapter of INAE. I will have, as you suggested, I will put on the slides, but I will just refer to that fleetingly. You want to, is the recording started? Yeah.
सुबह बता देते तो मैं कल से रेडी रखता ना। हाँ सीधा है वो तो पहले हमेशा ये हम लोग नहीं थे बहुत दिन से, फुल पिक्चर हम लोग के सामने नहीं था।
Can you see the screen? Is the screen?
Yes, we can see the screen. Definitely, we can see the screen.
So, as you have mentioned, Professor Basu, the title of my talk is India's Self-Sufficiency in Materials of the 21st Century. Now, when we say self-sufficiency, we of course mean that what we produce, we consume, or what we need to consume, we produce. That has, of course, a lot to do with links to the market, the Indian market. And you will see that sometimes we are actually limited in our leadership in materials by the Indian market. And one of the reasons for driving towards self-sufficiency is, of course, to be a world leader in certain areas, right? So if you hark back at the impact of COVID, it was clear that it brought to the front some of the loopholes in our society. It's the lack of statistics of workers, the lack of medical facilities across the country, so on and so forth. But what it also did was it resulted in a realignment across the globe. It was not very far back that. May I request all of you to switch off to be on mute, otherwise there's an echo. But please ask questions whenever you feel like. But anyway, so there was a realignment. It was not very far back, maybe about a decade back, when we were all talking about globalization. That everything that's available in one part of the globe will be available with similar quality and cost across the globe in any other part. But I think we're seeing a more localizing world where self-sufficiency is the mantra. We are also seeing that medical materials and devices are the need of the day, and how it is extremely important to be self-sufficient in those, especially when there is a calamity in the nation. And what is also then as a corollary brought to the fore with more strength is more impetus is the fact that we need to be independent, to be a power, to be independent in strategic materials. And some of the materials that you can see the screen, right? Still.
Yeah, we are able
Yeah.
to see the screen. Medical materials.
Yes, and some of the materials that that come to the fore are medical materials, energy materials, etc. So I will take examples of a few of the materials and paint a picture of where we are as a nation and what we can do to become global leader and be self-sufficient in those materials as a nation. Again, now, in medical materials, right at the beginning of COVID, it became very clear to us as to where we were. Yeah, the frontline workers used raincoats as PPE, and of course we quickly, as a nation, we quickly addressed that, and proper PPE became prevalent. And of course now it's taken for granted. But in terms of how our nation fares in medical facilities across the nation is clear to everyone. Um, Although we have a rising population and a rising aging population, the per capita spend on medical devices across the nation, in comparison to global average, is minuscule. In terms of reach of medical facilities, both practicing surgeons um, and facilities across the nation is also um, concentrated mostly around the cities and less available in the rural areas. Now, if we look at the market of medical materials in India, it is roughly about 60,000 crores per annum today. And these medical materials and devices are not medicines. They are devices that are that go on the body or in the body without any particular medicinal value. They are used as mostly structures or bandages or syringes or even diagnostic devices such as X-rays and all that. So this market in India is about 60,000 crores today and is increasing in double-digit growth rates. Roughly 75% of these is imported, and it's imported mostly from the West. There are a few big companies and big names such as Johnson & Johnson or Stryker, and some of it is imported from the East, especially from China. Can you imagine that this essential sector is so heavily dependent on imports, and therefore the prices that we pay for these materials is exorbitantly high. The Indian scenario of manufacturing of medical materials and devices is also fragmented. There are about 750 manufacturers. And predominantly, most of these manufacturers, 95% of them, have a turnover of less than 150 crores per annum. They are small, which means they can't invest much in R&D and technology, which means their quality is stuck at a certain level and is most of the time inconsistent. Basic materials such as hydroxyapatite, which is not a new material, it's available for the last 30, 40 years, but high quality hydroxyapatite that goes as bone supplement or even as bone cement in orthopedics is imported, or hydroxyapatite that is coated on implants is imported. stuff like collagen is even more rare. I mean, collagen is it can be used for to treat a high degree burn, or it could be also used in as food supplement. Is There are only about 9 producers in India, and not at very high quality, right? There are about 1 million high degree burn patients in India. Most of them don't get to access collagen because of the cost, because all the collagen that can be used for this purpose has to be imported. Now there are technologies in India which develop collagen from the usual cow or pig, which has its own socio-religious consequences and implications. There are technologies in India that use fish, which is much more friendly. But then we need to take these technologies out of ideation, out of laboratories into commercialization, and that effort needs to be made. Until that is made, we will continue to remain a country that is strongly dependent on imports, 75%, as I said. And with the growth of population, with the growth in the number of aged people in the population, with more affordability, this market is going through a double-digit growth, is seeing a double-digit growth. And imagine the pressure on the Indian foreign exchange exchequer in order to procure these materials and for treating our own people. And imagine the cost at which these materials and devices are procured. It is not as if basic knowledge in this area doesn't exist. It exists. There are groups in ISC Bangalore, in the IITs, or also in some of the CSIR laboratories, which work on medical materials and devices. But as I have described, the manufacturing fraternity in India, which needs to pull these technologies out from the labs into the domain, into the commercial domain, are fragmented and weak and small. So that link breaks. And therefore, we don't take our own indigenous ideas from the labs to the users and the hospitals. There needs to be a strong link. There needs to be a large Indian company that could come into this space and take Indian ideas into the Indian market. And there is absolutely no reason why these ideas won't work, except that one has to spend time and money in order to take these materials forward, go through all the entire steps of certification and all the trials, the animal trials, etc. But that has to be done. It has been, the Western countries are about 25, 30 years ahead of us. But so were those countries ahead of us in basic materials such as steel. You would remember that in 1990s, even the early 2000s, India made 30 million tons, 40 million tons of steel, when the world made about a billion tons of steel, right? Today, the world makes 1800 million tons of steel. China is roughly half of it. But India has grown. India is about 110 million tons, and at 110 million tons today, India is second in the world in steel. Similarly, India is third in the world in steel. It has happened because the consumption sector has grown, the infrastructure sector has grown, automotive has grown, and similarly, and of course, we have had large companies invest in these materials. Companies, one of them I come from, they have invested, they have grown in India, they've grown abroad. Similarly, you have some of the aluminium companies that have grown in India and grown abroad. So that growth has come and has made India a leading force in these materials. It perhaps is a matter of time, but it won't happen if you just hope. Some big companies have to come in and do exactly what has been done in steel and aluminium in these very, very important and socially relevant sector. Let's look at aerospace. So this is how material use in aerospace has changed. I'm looking at Boeing and Airbus. The latest Boeing in the air is 787 Dreamliner. The Airbus double-decker Airbus that you see is A380, but the latest is A350, which is not a double-decker. The use of composites is what is to be seen. The 787 Boeing and the A350 Airbus use more than 50% composites in the body. This has resulted in drop in the use of aluminium, which was earlier about 70 to 60%, 60 to 70%, has dropped to around 20%. And the main reason is that mostly carbon fiber composites and aluminium don't sit very well side by side. There is a huge corrosion issue, and which has led to the increase in the use of titanium. Right. So there's a huge demand of titanium in the world, a huge demand of carbon fiber in the world. And how do we fare in these materials that are used in aerospace? And India has a dream of being big in aerospace. You're familiar with news stories of Boeing and Tata coming in and setting up aircraft manufacturing facility in India. India wants to manufacture its own lightweight combat aircrafts, the LCA program. We will need lightweight materials and materials such as titanium and carbon fiber. But let's look at these materials and how we fare compared to the rest of the world. In titanium, we have the third largest deposit of titaniferous ore along the coast of Kerala, Tamil Nadu. Yet we make about 500 tons, which is less than 1% of global production of titanium. And that too, we make in one plant, and 500 tons is suboptimal. So obviously the costs are way above optimum. It has also no magnesium recycling facility at this scale, and therefore it remains a demonstration plant perhaps, but not the titanium that comes out of this is commercially not viable. This needs to be scaled up. And it needs to be scaled up for a market which is growing in India. The automotive market, the gears here show the automotive market is growing in India. Aerospace market is growing in India. Titanium is used in medical, in devices that are implanted in the body, either dental or hip implants. They all use titanium. But while we export titanium dioxide, which is made from the titaniferous ore that we have, we import all titanium alloys, mostly the Ti, ALV alloys. Now, if we look at the value chain of the knowledge value chain of titanium, I showed one for the medical materials. You'll see that there are multiple gaps that exist in India. There are very few research centers that work on titanium. There are more places that work on medical materials and devices. There are more startups that are coming up in medical materials and devices, but not so in titanium. So the churning of knowledge is limited. There are, of course, pilot plants and pilot facilities available. I'm sure you're familiar with them. But then again, the same story as in medical. There is no large company or no large manufacturing facility that can upscale titanium in a commercially feasible manner, which makes India lag behind the rest of the world. But then it's a chicken and egg story. India's aerospace sector has been so far, and still is only growing, has been so far a small sector with not enough pull pull for the technologies and not enough pull in the market. But then I think we need to change our mindset. Our market cannot just be India. If we need to be a world leader, if we need to be self-sufficient in a particular material, we need to treat the world as our market. And it's only when we treat the world as our market, we will produce at global quality standards. And that's what it will make us leaders as well. And once this pull comes, the rest of the value chain will also fill in. It will drive investment into R&D. It will drive investment into basic research. It will fund research in titanium in universities and research laboratories. The other material that we spoke about was composites. Let's look at where we are in composites. I'll fast forward a bit here. You are familiar with composites. The world market of composites is about $95 billion, and this includes both glass fiber and carbon fiber composites. Indian market, at a very not so conservative way, in a very benevolent sort of picture, is about $4 billion. I personally think it's about $2 billion. But it's growing. It's growing in India as well as growing in the world, and it's growing because of the key properties that composites have: lightweight, superior strength to weight ratio, corrosion resistance, and excellent design flexibility, which metals can't provide. And therefore, we can make, we can compete with metals on multiple sectors, in infrastructure sector for poles and pipes and bridges, for street furniture, for chemical tanks, and of course also in marine and defense. Right, this is a railway compartment. The interiors are transforming into composites, and so on and so forth. Let's look at the composite material that is needed for aerospace, carbon fiber. Right. Today, the world is increasing in its production of carbon fiber by leaps and bounds. Right. The world makes about 750 tons of the world makes India consumes about 750 tons of carbon fiber. Not the MT, there is not million, it's just metric tons, which is roughly 1% or even less than the global consumption. The same story as in titanium, where we have the third largest deposit, but we make less than 1% of the world. Here, carbon fiber, we consume less than 1% of the world, and it's essentially because the market was small in India. It's growing, but do we have the technology ready to supply to that market? The answer is no. The traditional way of making carbon fiber is from a polyacrylonitrile route, which is a petroleum product. The technology involves carbonization of the polyacrylonitrile and drawing them into thin, less than 10 microns thick for aerospace, around 50 microns or less for construction space of carbon fibers, and they can then be bundled together to form toes, as they say. Now, a large part of the cost of carbon fiber is in the precursor, which is polyacrylonitrile, as I said. Of course, there is labor. Now, there is technology available and it can be developed where the precursor is not polyacrylonitrile, but coal tar. Now, we have a lot of coal tar that comes out of our steel plants, and our steel sector is increasing in size. Properly treated, coal tar can give a precursor that can make carbon fiber. Now, if we have that technology ourselves as a nation, we then have a huge raw material benefit. We have a cost advantage because that coal tar comes out as a byproduct of the steel making process, of the coke making process. And we have indigenous technology with indigenous raw materials. So it's worthwhile spending money and developing carbon fiber using coal tar, with coal tar made from the coke ovens of Indian origin. Now let's look at where we stand in terms of the knowledge value chain of carbon fiber. As you would know, there is very little work that is going on at the basic research level in carbon fiber. There are very few groups. They are disparately spread, very little funding. There is only one pilot plant in India at NAL Bangalore, which works on polyacrylonitrile-based precursor. Some people have, in all fairness, tried to take that pilot plant and upscale, have not succeeded. But then again, the manufacturing scenario on composites in India is again very similar to the medical material scenario, where it's all fragmented, small players, can't spend in R&D, and therefore the situation remains status quo. The Indian market, which is essentially the aerospace sector as of today, the HAL, the Tata Boeings, they depend on either the Japanese suppliers or the American suppliers for their carbon fiber. And this space in India is increasing, and we do not have today a technology that is indigenous, that we can call Indian. So I think in this area, a national focus is needed, where we can use nationally derived precursor, where we don't have to depend on a foreign country for the precursor. It could be coal tar, and we can convert that coal tar into carbon fiber with high strength and thicknesses less than 10 microns. This is eminently possible. Some of the work that we have done in Tata Steel has shown that we can actually spin carbon fiber out from processed coal tar. Strength levels up to about 700 megapascal, but then it's still at less than pilot scale. It takes time and money to upscale, and I think these are areas where we can work together as a nation with a national focus to produce indigenous carbon fiber for the indigenous industry. Let's look at some of the strategic materials. Photovoltaics, right? The cost of photovoltaics has dropped significantly over the last 10, 20 years. But do we have an indigenous photovoltaic material that we can call ours? No, we depend on China for the polysilicon, which goes on to make either the single crystal photovoltaics, silicon-based photovoltaics, or the polycrystalline photovoltaic material. Do we have a SIGs that is indigenous? We don't. Do we have perovskite of our that we can call our own? We don't. Our investment into photovoltaics is again disparate. And if you look at the cost structure of producing silicon-based photovoltaics, you'll see that production of polysilicon from quartz upwards involves huge amount of electricity. And the cost of electricity in India is still high. And it's also a state subject, so the cost of electricity varies from state to state. China makes about 90% to 95% of the world's photovoltaics, mostly silicon based. The cost of their electricity is less than a cent per unit, or around a cent per unit, which makes it maybe unfair in the global market, but it has helped China to flood the global market and capture the global market of photovoltaics. Energy materials. India depends entirely on, of course, mostly on imported oil, 83%. And we know that the move towards electric vehicle is a one-way street, to use a pun. It's a one-way street because driven by environment, petrol or diesel IC engine vehicle will give away to hybrid or battery or fuel cell driven vehicles. Now, if we have batteries, how does it help the nation? The battery materials are lithium, nickel, cobalt, or electrolytic grade manganese. None of these are produced in India. Lithium are sourced in Chile and most of the mines are owned by China. cobalt, Congo. Nickel, again, not very rich in India. Needle coke, and which is mostly imported from China. But here again, and I'm sure Professor Basu's IMMT has worked on this in this area. There is possibility of developing technology which will use Indian raw materials to extract nickel and cobalt from lean ores. So there is need for developing technology which can treat overburden of chromite ore, which has around 1% nickel and around 0.1% cobalt, to treat vast amounts of overburden to extract the nickel and the cobalt and enrich them for use in batteries for Indian vehicles. The manganese ores that we have around the same area in Orissa can be purified to make electrolytic grade manganese, and India is probably one of the highest producers of manganese in the world, but it doesn't produce a single ounce of electrolytic grade manganese. But it's possible. And in terms of in lithium, it is extremely important that we have our own urban mining system where we can recycle and regenerate lithium. The amount of overburden that we have in our country, the chromite or overburden, can roughly substitute 50% of imported nickel and cobalt by the year 2035. That's a huge saving on the exchequer. And I think that's a technology. Today we have about 13 to 15 years left to develop this technology. And I think it's worthwhile, again, to invest in this technology as a nation to develop ways to extract nickel and cobalt from the overburden. I think when we go to rare earth materials, it's important that we develop proper urban mining systems in our country. Today, the scenario is, as is shown in this picture, it's very manual, very dirty, very fragmented. It depends on, it's mostly restricted to collection, separation with manual effort, and perhaps some amount of initial melting into ingots. And then further metallurgical processing of ingots is majorly not done in India, it's sent abroad. So when it comes to the final value extracting step, it's not in India. Whereas we can extract gold and all the rare earth materials and nickel and cobalt and copper, we either just sell the scrap or we convert it into just an ingot and send it abroad. I think it's important, and it's good to see that very recently the government has come up with a paper on urban mining, and few centers have also been selected for concentrating urban mining activities in the 4 regions of India. But I think there is a huge amount of work that still needs to be done at the fundamental science level and also at technology development level. And again, I'm aware that Professor Basu's lab has already done some work in that area, and so has National Metallurgical Lab in Jamshedpur. Similarly, there is enormous need to work on magnetic materials to extract and reuse elements such as neodymium, etc. I will just touch upon some of the materials which are new to the world, and India is positioned to take leadership in the world. One is graphene. So I would just say that Tata Steel has about 20 intellectual property rights in terms of patents and design registrations in production of graphene using 2 routes. We use graphene rubber, in polyurethane, and HDPE. So we enrich the properties of the compounds that make the products. We use we deliver master batches for use in these products, and also make paints for corrosion resistance, paints that go on steel structures for corrosion resistance. Last year, we set up 100 tons per annum capacity graphene plant, which is one of the largest plants in the world. And today it's functioning and producing all the graphene that we need to produce the pipes and the conveyor belt and the master batches that I showed you earlier. I will skip over this. I will just mention that in some of the areas, in some of the areas, Tata Steel has taken steps to bridge the gaps in medical materials. We have just set up a business in medical materials where we will be producing, and we are producing hydroxyapatite and collagen. We have just set up a company called Tata Ceramet that will focus on advanced ceramics, including hydroxyapatite. But what is most important as a nation? A single company can do things. We are also working in the area of composites, in developing a business around composites. But what is more important is to have a national focus and a national ecosystem to develop a holistic approach in materials for this 21st century, and to take leadership in the world. If we look at what other countries have done, let's look at Germany. Germany has a system of Fraunhofer institutes, which I'm sure you're aware of, which takes ideas from technology readiness level of 1 to 3, which is in the universities, develops them forward to the pilot plant level of technology readiness 4, 5, 6, and handholds that with an industry to take it to the market, technology readiness 7, 8, 9. And that happens because the Fraunhofer institutes are funded 1/3 by, most of the time, 1/3 by the local government, 1/3 by the state government, by the central government, and 1/3 by the industry. And this is most of the time large industry like Mercedes or Volkswagen and people like that. The industry gets new technology, innovation, and can commercialize that very, very quickly at 1/3 the price, 1/3 the cost that it would have otherwise incurred. The caveat is that it has to come along with an MSME, a medium to small sector industry. It's extremely important for a nation for the MSME to be enabled to become innovative. MSMEs across the world don't have the financial resources to invest in R&D, and R&D is expensive. So the structure is so designed that the MSME, which are mostly ancillary suppliers to an industry, is brought along by a large industry, is made a partner in the development of the technology. The Fraunhofer system is such that the Fraunhofer Institute is either in or next to a university, so there is a closed link and even crossing of manpower. So senior researchers at Fraunhofer are professors at the university and vice versa. So in that way, they overcome the major valleys of depth in the innovation system, the depth between ideation and pilot, the valley of depth between pilot and commercialization. India's structure, of course, this structure, German structure, has been copied by multiple countries. The UK has, for example, set up the catapult system, right? Where the catapult centers are focused on certain technologies, and they are again residing next to or inside a university, and there is government funding that comes in if there is a proposal together with an industry. And again, that whole system helps in bridging the valleys of death and accelerating the progress of the nation towards higher technology and innovation. India has the elements in place. It has excellent academic system through the IITs and ISCs and NITs. It has gotten a very strong CSIR labs, collection of CSIR labs, which have excellent manpower, have facilities to take ideas forward to pilot. Where the country lacks and can be strengthened is a system, a funding system that will bring industry, CSIR labs, and the academics together on focused, themed projects. It could be in carbon fiber development, it could be in robotics, it could be in, and if I just concentrate on materials, it could be in medical materials, it could be in titanium. And there is enormous field of areas in which we can, where we need this whole troika, if you say, the academia, the CSIR labs, and the industry to be brought together by a thread of government funding to help the country develop an ecosystem where the valleys of death can be bridged effectively. And I think this is fundamental to take our country forward in the world, to be a leader in focused areas that we need to be leaders in, and to be self-sufficient in some of the materials that we think the country needs for the future. With this, I would say thank you very much for giving me this opportunity to speak, and hand the session back to Professor Basu.
We have a couple of questions. First is, what is the current status of special steel in India for specific domestic industries, and what are the future for exports?
I didn't quite follow the question. Sorry, can you please repeat it? Your voice was breaking.
There is an echo. Echo can be stopped if everybody switch off their microphone. Now I can see that it is. So what is the current status of special steels in India for specific domestic industries, and what are the future export potentials?
Right. Good question. So the 110 million odd million tons of steel that India produces, most of it, almost all of it is consumed internally. India exports very little, also imports very little. Yes, it's net zero. What it imports is very specialized steel for which the markets are limited. So, for example, CRGO, cold rolled grain oriented steels for transformer applications, the high-end CRNO, which today would be used in electric vehicle motors for high-speed revolutions and noise-free revolutions. But then the market today is still small. Right, so these steels and some of the high abrasion resistant, high hardness steels, which some of the Swedish companies make, so those niche products are imported into India. What India exports is mostly opportunistic and some of the line pipe grades across the world, right? But again, it's not voluminous to have any serious impact. So India makes India's domestic production is largely construction grade steels, going for construction, rebars, angles, channels, etc. Quite a bit of line pipe grades, and of course automotive grades. Yeah, with the increase in the volume of automobiles produced in India, the demand for automotive steels has grown, It is a high demand in terms of quality and surface quality, especially surface quality as well as deformation characteristics. And those steels are now being made in India, except for the very high end, very high strength and toughness combination steels, such as the press hardened steels. Those are today limitedly manufactured in India. Otherwise, India makes what it wants, what it needs, rather. As the market grows, India's production and the range will definitely increase. India has the know-how and the capability to make CRGO. It's only the market that limits it from putting up or any of the steel plants from putting up a mill today. So I hope that answers part of the question.
I have a question. I mean, of course, you have nicely pointed out the stories and why it is not working in some of the areas, which should have done much more work. And one of the model that you said is the Fraunhofer model. Other one is a slightly different but similar, is the catapult of UK. But is this the only way to look at it, or is there any other model where people can work, whether it's different from these two, whether China, Japan, or Korea or US is doing little different or something different that India can look upon, or it is the only way to go forward?
Of course, there are many roads leading to Rome, right? So there is a Chinese model, and of course, I don't think we can follow that model. The pump in resource, amount of resource is, I don't think we will follow that way of pumping resource into certain areas. So, for example, one of the universities I'm associated with, University of Science and Technology, Beijing, is a. Sorry, there's a noise. Thank you. So that the university is almost entirely dedicated to iron and steel research. It's a university which has more than 300 PhD students, all working on various aspects of iron and steel. More than 92 postdocs, right? And they work not only at the fundamental research level, they actually also work at the plant level. So they have automation capabilities, so their programs would be running in Shanghai in Baosteel, and they would be monitoring the effect and how the program is running in their lab in Beijing online in real time. And of course, that needs years of building that system, and not only the infrastructure system, it's the entire ecosystem. It also needs money. And roughly the budget of that particular university is $1 billion per year. Now, setting that aside, right? Most of the other systems are some form of the troika that I have mentioned. If you look at the Korean system, right? POSCO, which is the biggest Korean steel maker, set up POSTECH, right, which is university. But what we don't know is that largely it was actually funded by the government. It was almost a 50-50 funding. So it looks like a POSCO university, but there's huge amount of government funding that comes in to set up, because you're developing the nation by developing infrastructure and people along with it. In US, it's the same. It's the funding that comes from the National Science Foundation or the Department of Energy, the Department of Defense, that goes into large laboratories, which are also associated with with various universities. So for example, NREL, right? I showed that graph of photovoltaic, which is something that NREL publishes every year. The National Renewable Energy Laboratory. Right? So they produce. So the funding from, say, the Department of Energy goes into NREL, and NREL has its own research staff, but it also funds the neighboring universities and the collaborative universities for carrying out research. Right. So this model where government funding acts as a
You got muted. You got muted somehow.
yeah.
No, again you are muted.
Is it happening centrally?
No, we are not doing anything.
Okay, sorry. So where was I? Yeah. So there was this. So the funding is, and the nature of funding and the criteria associated with the funding are fundamental to determining how collaboration happens between academia, research labs, and industry. So there's no getting away from it that you need to have the troika, but the troika is brought together by government funding. And one of the reasons of government funding is to take away the risk associated with large technology, developing large technology. It is expensive. So again, one of the big examples is Nucor. Nucor is an American steel company, almost as big as Tata Steel. They set up the first twin roll caster, which was a new technology at that time, and it was high risk at commercial scale. But then once you do that, somebody has to take the risk. So it was the US government pitched in a large fraction of the cost of putting up the first twin roll caster to take part of the commercial risk of a new technology. So I guess it answers partly your question.
Yes, definitely.
Continuing on this.
Yes, please.
Yeah, you said in China as well as in United States, the government funds. Okay, that is fine. You are looking at it like that. But where does the government get the money from? So, Americans sell arms and they get money. I don't know about China too much, but America sells arms to both the contestants and gets money. Airplanes, basically. So where do we get the money? Where does our country, our government get the money? We pay income tax, but that is in rupees and that is peanuts.
I don't think I'm qualified to answer that question, if there was a question.
Yeah, it's a larger, complexity.
But I think it's a matter of policy, more a matter of policy than anything else.
Is there any more question?
One question. Hello, Tripathi here. Just one question. I mean, do you think the scientific community is confusing the government in several issues? Like my experience, I can tell, when the progress in scientific research is going on, we give a feedback to the government that progress is very good and we are on the verge of doing something. You give X amount of money and it will be done next year and all that. At the end of the day, after a few years, they are either too late for the market or they don't come out with a product, commercial product. Then they say, raise their hands and tell that we have been telling government to have a change policy. I'll give you the example of silicon. After so many years and so many places where it was told that ingots cannot be made here, material is not available, and chips are definitely required in India to be in the electronics field. The government will listen to people, spend a lot of money on nanotechnology, But finally we said, no, it cannot be done. Then international tender is now floated and government is telling that we are going to spend large amount of money in silicon manufacturing and we are already late and people will ask their own price to do it. So are we confusing each other? I mean, with a frank question, please answer from your experience.
Yeah, so, you know, we as a nation have always tussled between make and buy. Where buying was not possible, we have actually made very well. And the examples are ISRO and atomic energy. We are entirely indigenous and we are world leaders, right? So it's not that anybody got confused. It's just that we decided and we had to decide to make, and we made extremely well. But somehow, when it comes where we have an option to buy, we always buy instead of make. I think that's a policy shift we need to have, and at some stage, when it comes to self-sufficiency, where being self-sufficient will become strategically important, necessary, not even important. I think all these confusions will go. There is no confusion. I think when proper review is done, there is no confusion. So, and I'm sure when the necessity comes, we'll make well.
Thank
As
you.
I said, the building blocks are in place. It's a matter of policy to put them together. I don't know if that answers your question.
No, thank you. It's a good answer. And materials field particularly, I find all the research taking place are reinventing the wheels, characterization and all that. Everyone gets a PhD in India and repeating somebody else's work outside, apparently. And once in a while, breakthroughs are made and people are coming with good results. But 95% of the work done in normal institutes, ordinary institutes with limited funding, as you correctly said, fragmented funding, fragmented effort, no innovativeness, and then end result is what we are facing. Material problems are well known for years today. And then you said that big companies should put their hat on the and then come forward. Tata is doing very well. So should we stop this small funding and other things and then concentrate on large funding onto large manufacturers? And you never know whether they will develop it or whether they will import and sell it. Importing is the easier option, yeah.
Which is the buy part. No, yes, there is a policy issue, but I think even if you are incrementally improving upon existing knowledge, as you mentioned, through the current levels of PhDs, etc., it is still developing a trained manpower, right? A manpower that is trained in that direction. Yes, maybe it is not producing an MIT graduate or MIT PhD, but you don't always need an MIT PhD, right? It is creating a platform. It's creating a mass of people on which you can then build when the nation needs the next jump. Today, the quality of manpower that we have is, if you look at Southeast Asia and Middle East, anywhere other than Western Europe or Eastern part of the world, we are amongst the best, right? We are amongst the most powerful in terms of, and our people, no matter where they have got the PhD, can go anywhere in the world to do a postdoc, right? So the basics are being built, and that is not a mean thing. It's a substantially important thing. When we get the act together for the way the Western Europe, US has got, or the eastern part of the world has got, at least we will have a base on which to build. It will not be ab initio, right? So I think what we're doing today is important. Maybe it's frustrating to a certain extent, understandably so, but I think we are building a base for the country. And as I keep on repeating, so it depends on when the policies come in place, we will have a launching pad that is ready.
Thank you, sir.
Professor Renu Sharma, would you chip in and?
Thank you, sir. Thank you so much. Thank you so much. I find Dean IVSAH. Professor, you would like to ask some questions? Please unmute, sir.
Hello. Yeah.
Hello.
Good evening, everybody. And, wonderful account of research and development in metal and materials by the speaker. Many things are new to me because I'm a scientist working on viruses. But our deficiencies in the medical materials or medical units or systems, certainly we lack a lot, being self-dependent. And the professor has given an account in such a way, sometimes it is alarming. Say hydroxyapatite or photovoltaics. These are old materials. I mean, maybe 25 years old. Still having a substantial use in the system, in the society. But still we produce less. Still we produce less. Sir, do you think it is all about funding? Because in India, R&D is mostly government funded. Because I have seen, because I have been a director in ICAR Institute for a long time, who is having the all financial and administrative powers. I have seen that getting enough funding, even to construct a biosafety level 3 lab, say, from where the virus cannot leak out, have a RCC with a crack of less than 5 micron, the structure, which needs lot of input. But what I've seen myself, if the scientist or the director of the group is able to convince the government or the policy makers, I don't think there is any depth of funding. That's also holds true because new materials could be metallic, could be non-metallic. That is the future, and you know it better, and the material science. So why you do not sensitize the government? Because you have national academies in different physical sciences, different life science branches, everything. And the material is one thing which is required for all sciences. It could be material science, it could be life science, it could be biological science. Use of material in different form is of utmost importance. Say a pair of bird scissors, a pair of titanium scissors, a pair of titanium forceps, a titanium rotor, and you say the titanium we have in India plentifully available, maybe unable to get the final product. Similarly, lithium. And the current scenario in Ukraine, also Ukraine, they say Ukraine is very rich in lithium. Also Iran. So, sir, as a scientist who was interested in different materials, because even getting the plastic waste, polyethylene, polypropylene, polycarbonate, we need a material to store water which doesn't leach out ions. For ultra pure water, say in a very specialized laboratory, maybe IIMT everywhere, you see everybody has a overhead water storage. From that water comes to the RO system. From RO system, it goes to another storage. And in that second storage after RO, the material should be so that ions should not be leached into the water and making it harder. So we have application of material, either new or old, in every sphere of life, including laboratory or anywhere, including electron microscope. So, sir, my take is that maybe we lag back in sensitizing the government. As a think tank, like your Professor Basu in CSR, IMT, you are luminaries in your whole field. And that is really money. Material is money. So, sir, can you not take any steps so that the government increases funding?
Yeah.
Yes.
May I respond?
Thank you, sir. Thank you.
Thank
My
you.
query is not any question to you because I'm not qualified for that.
No. It's what the point you've made is extremely important, and I think I've given talks all over India. Nobody has brought this point up. You're the first person who's actually bringing this point up. I totally agree. It is a responsibility of the fraternity, of the materials fraternity, to also sensitize the government and bring these issues in focus. and this is being debated lately. So few years back there was so effort is being made in this direction. So a few years back there was a white paper written for the defense materials in defense. Very recently you'll see a similar paper coming out from Indian National Academy of Engineering, and I'm one of the editors of that. So on structural materials, advanced structural materials in India, the landscape and what is to be done. Also in Indian Institute of Metals, which is one of the premier professional institutes in the area of metallurgy and metals. This year, we have taken up an initiative where thematic groups will be formed amongst eminent scientists and industrialists in focused themes. And the first focused theme is recycling. Right? And the idea would be to create documents which would be of the quality and impact that could be put up to these principal scientific advisors, say, who can be influenced, who can then take the debate forward into the government cycles. So while there has been an increasing effort in writing these white papers in materials, with the Institute of Metals coming in and creating an initiative to on thematic thematic groups, I think this will gather momentum over the years, over the next few years. And what you're saying is exactly the role that that the Institute of Metals will play in creating awareness at the principal scientific advisor level in the Ministry of Science and Technology, and then help that discussion to percolate through the government. Very important point, Professor.
Thank you, sir. Thank you so
Thank
much.
you, sir. Thank you so much, sir. Now I'll invite our Pro Vice Chancellor, sir, for this giving the vote of thanks to our guest. Please, sir.
Good evening. It's my privilege to extend vote of thanks to Dr. Devasys Bhattacharya for his nice presentation and projecting the whole material science, need of material science for sustainable development goals of the country and in the line of the whole world and the UN mandate. And not only that, he pointed out very lucidly the need and the emergence of some of the kind of the materials for different fields of applications for coming decade, and the capability of the Indian community he lauded, and also the kind of the bridging synergistic effort needed to come to a level of success as per the West, and I think invited a lot of discussion. So therefore, on behalf of INAE local chapter and SOA and IMMT, I once again thank Dr. Devasys to, I think, project the picture of the material needs, the needs of the research as well as the development in material science for growth of our country in general and regional in particular. Thank you very much for your time and for sharing your expertise and experience. Thank you.
Thank you for the invitation. Hopefully it was useful.
Thank you, sir.
Thank you, sir. Thank you so much.
Thank you. Thank you.
Thank you, sir.
Namaste.
Thank you. Can I log off?
Yes, please.
Thank you. Wish you all the best.
Thank you.